All right. Good morning, everyone. So please be aware that now this is all working under a couple of assumptions. We're operating under the assumption that we're going to complete 1.7 today. And with 2 hours, you would hope that that's enough time to complete it, but there's a decent amount of material, and because of that, a decent amount of examples I want to cover in this section. So I'm going to try and finish it today. I hope we finish it today. And if we do finish it today, then everything else up here is correct. But you'll notice there's a big if here. So if we finish 1.7 today, it's due in a week. We'll definitely finish 1.8 next in one class. So that should be completed by Tuesday, and then that could be due the following week. And then assuming that we have all of Chapter 1 completed in a lecture by the end of next Tuesday, this coming Tuesday, the 9th, then that puts Test 1 on Chapter 1, the 16th through the 18th. Now, normally tests are single days, but as I've said before, because I know we're on different schedules, some of you could be in like a parking lot, getting internet just to do this stuff. I don't know. I want to give you a couple of days to be able to do this, generally 2, 3, maybe 4, depending on the circumstances, but 2 to 3 is generally where I want to keep it for a summer class. So again, this is all assuming that we have finished a chapter of material by the 9th, not the 8th, 9th. In terms of what the test will look like, you should have 2 hours to complete it. It'll be 20 questions. I'm going to give you 2 attempts for this first one. I'm not promising that I'll always do this moving forward, but on the first test, while we're still getting used to things, I'm going to give you 2 attempts. So, and then I take the best. Not the second one, it's not the first one, it's whichever one's higher. If you only take it once and then the due date passes, no, you do not get a second attempt. So if you're happy with your first attempt, that's good enough. If you don't like your first attempt, you can study and then get a second attempt. There will be a review. There will be review materials for the tests, and they'll be presented at least a couple of days before the 16th. But we'll, as we get closer to that, we'll iron things out. But for now, we need to move on into 1.7. Lots of space. Chain rule. Okay, so the chain rule is for what we call composite functions. When we want to take a derivative of a function that feels like it has another function inside of it. So you've been through pre-calculus, you should all know what a composite function is. If you had me, I call it the chicken cordon bleu of math because it's one thing stuffed inside of another thing. But in math, it doesn't have to be chicken cordon bleu with ham stuffed and ham and cheese inside of chicken. You could actually go the other way and put the chicken inside of ham and cheese. You can also put chicken inside of chicken and ham and cheese inside of ham and cheese, because it doesn't matter how you compose functions. It's just what matters is that you can identify the composition and then do some stuff with it. So this is going to be, again, for functions where there's like an inside and an outside. So this, I thought I hit Control U. This is for taking the derivative of functions that look like they have insides and outsides. That's the way I like to kind of describe it vaguely. Like there's one function inside of another function, and you can see it. Now, I just want to put a few things to paper that I've said. Chain rule requires some composition knowledge. Given an f of x, g of x, the compositions generally seen are fog, which is really read f of g of x. When I say fog or golf, I'm just being silly. F of g of x. And this is the composition notation, which honestly, I don't even know why mathematicians use it. I've never figured that out. Why not just do it this way, which is f bracket g of x? And the bracket could be an extra parentheses. So these brackets could be parentheses is what I'm saying. It's just the g of x is the inside function, the f of x is the outside function. So we'd be putting the g function inside of the f function. It's kind of like when you have f of 3, it tells you to plug 3 into the f function. This says we're plugging g into the f function, something more complicated. Or the other one that's very popular, GOF, g of f of x, which would be g bracket f of x. You can do f of f, you can do g of g, and that's what I was referring to with the ham and cheese and chicken. You can put chicken inside of chicken. You can put ham and cheese inside of ham and cheese. You don't have to put one inside of the other thing. You can have a pile of chickens, you can have a pile of other chickens, and you take pile or chicken 1 and put it in chicken 2. It's the weirdest chicken cordon bleu you'll ever have. It's like a turducken, but without getting different birds. But you could still do it, and I bet there's a chef that's done it somewhere. All right. So normally we focus in a pre-calc class on taking one function and stuffing it inside of the other, but we're going to take a different approach. So in pre-calc, we end up stuffing one function inside the other. But in calculus, we tend to focus on looking at one function and making it a composition, determining inside and outside. So our goal is to write the original function as sum f bracket g parentheses of x. Bracket looks a little funny typed out. That looks a little better. Where what we call g of x is the inside and f of x the outside. Now, your original function may be written as f of x, so maybe you want to use different letters. Maybe use g and h and call g the outside and h the inside. It doesn't matter what you call what, as long as you have the idea sound. And there's a nice trick that I like to use. This is very helpful. When you're writing the outer function, replace whatever would be the inside with x. Now, I wrote that as a capital X for emphasis. It doesn't have to be capital. It can be lowercase. I mean, a lowercase x looks exactly like an uppercase x, just smaller. So again, the trick is when you actually go to write what you're going to call the outside function, replace what you would call the, and I'm putting air quotes with my fingers, the inside with an x. Do I really have to have these quotes around inside and outside? Not really, but I just feel like because there are arguments for what the inside could be and arguments for what the outside could be, that I need to use those little air quotes. So before we actually get into the calculus side of things, let's practice looking at one function and turning it into a composition, finding out what these f and g's would be, because that's what we're really going to have to focus on the calculus side of things. And depending on who your pre-calc teacher was, you may have seen something like this before, you may not have. Depends on where you took the class and who your teacher was, like I said. So example 1. Given a function, I don't know why I'm handwriting this part now, but it's fine. Write it as the composition fact, I'm going to type it. Click, 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 click. Given a function, write it as the composition f of g of x. So for a, we're going to be given the function the square root of 2x plus 3. So there's our function, and we want to try and figure out what you would call the inside and what you would call the outside. And I think it's pretty easy to see what you'd call inside and outside based on this. The inside would be the inside of the square root, and the outside would be everything else, the actual square root itself. So the inside is the 2x plus 3. The outside, and now the inside is what we call the g of x, because that's what's inside the composition. The outside is the square root part. Now, some people will write square root and then they'll actually write the word inside here, but I don't really like to do that. I said that there's a pretty good trick with this, and this is especially important when we're getting to the calculus. When you're writing the outer function, which is what we're doing right now, replace whatever would have been the inside being the 2x plus 3 originally, instead of writing that 2x plus 3 where we identified it as the inside, just write it as an x. And I'm even going to use color for emphasis here. So that red x, the red x represents the inside. And I'll try and use the color for emphasis for a while. Because this red x, if you were to plug this inside, if you took this, which is the inside, if you plugged it into the variable of the outside function, you would end up getting the original function. And that's exactly the idea of a composition. It's taking one thing, putting it into another thing, all of its x's, and then you get something else. And the something else would be the original problem. So just for checking this, this is going to be the only one I check. This is literally going to be the only one I check. What is, and by the way, I forgot to write it, but the outside function is the f of x. Inside is g of x, outside is f of x. So if you were to do f of g of x, this is math you're supposed to know. Go back to the chapter R stuff if you're rusty and find the composition materials, but you plug the inside function in first. So we do f of, and the g of x, the inside was the 2x plus 3. So we're supposed to be taking f of 2x plus 3, which says we go to this function. So we're going to this function, but wherever we see an x, we're going to replace it with 2x plus 3. If this said f of 3, it would be the square root of 3. If this said f of 2, it would be square root of 2. But it's f of this thing, kind of like an f of x plus h, so we turn the x's into, instead of x plus h, well, 2x plus 3. So this would be the square root of, here's the square root from the outer function, from the f, and then instead of the red x, we write the inside of the f, 2x plus 3, which is exactly the original function. Now, here's the fun part, is that the original functions are generally denoted as an f of x. So instead of writing f and g, what you'll see me generally write are just the words inside and outside. Because if your original function is f, I can't call the inside or the outside f. I'd have to call them g and h. And there's nothing wrong with that, but a lot of people would instinctively write f. So I tend to write in and out. Okay, so let's do another one of these. B. Parentheses, 2x to the third plus 5x minus 3 raised to the 6th power. Same goal, write it as a composition. So we need to figure out what the inside function is, what the outside function is. So the inside and the outside with practice becomes a little more clear, but it's generally just looking for, okay, what's the complicated bits that could be separated as an in and an out? And it's generally the inside of a square root or the inside of a parentheses, or maybe the bottom of a fraction if the top is of a specific format sometimes. So what I would call is the inside of the parentheses, which the inside of the parentheses is the 2x cubed plus 5x minus 3. So that's what we call the g of x if our composition goes f of g. If I was doing g of h, then I'd call this the h of x. Making the outer function, the outside, well, that's the parentheses to the 6th part. So it's all of the inside raised to the 6th. But instead of writing the inside, you just write, and again, you could write it this. Some people would write, it's the inside stuff raised to the 6th power. But I don't like doing it that way. I like to use my little trick where I write an x representing the inside. So this red x, I feel like I have something extra here. This red x represents the original inside. It represents 2x cubed plus 5x minus 3. This is our outside function f of x. And if you put the black g of x inside this red x, you would very quickly get the original problem, the original function. Let's do a couple more. C, we got the cube root of x cubed plus 8, and then a minus 5 outside of the cube root. Just a little more going on with this one. Does that complicate what we would think the inside and outside are? In my opinion, no. But the outside function isn't going to be as simple as previously. So the inside, again, is typically insides of things being raised to a power or square root, which is literally something raised to a power. Sometimes it's an entire denominator, depending on the format. Sometimes it's an entire numerator. It just depends. You could see these insides in multiple places. Maybe you only see them in one place and it complicates things. All right, so the inside, well, we've got this root, so I'd probably say the inside is the inside of that. So the inside is probably the x cubed plus 8. So that's what we would call our g of x. And then our outside is everything else. Just what we called the inside is now a red x, and you go back and you write the original function, but instead of writing the x cubed plus 8, you just write the red x. So our outside function, it's the cube root of x, then a minus 5. See, the red x is representing this right here. The minus 5 still has to be there. It's not part of the inside. It's something completely outside of that. And if you were to stuff this x cubed minus 8 into the x here, you would get this original problem, this original function. Looks like a Madden drawing. Uno más. One more, por favor. Square root x plus 3 over x minus 6. So again, we've got a square root and there's a fraction inside of it. Now, whether that's acceptable or not in terms of algebra, we're not worried about. We're just worried about making this composition. So the inside is probably just the inside. I wouldn't call it just the top or just the bottom. I'd call it the whole inside. And again, I've said that there are times where you might call an inside the bottom of a fraction. That's not what's happening here. So the inside is the x plus 3 over the x minus 6, which we call our g of x. Making the outside function the square root, but instead of writing any of the inside stuff, that's just a regular old x now. And that's what we call our f of x, which I did not write on the last one, but I did say it. This is absolutely critical to have as a skill. Otherwise, without the algebra, which is what this is, you can't do the calculus. Calculus is just formulas. That's all calculus is. Formulas and word problems. Hold on, I need a minute. Okay. Enough space? Yes, we do. So now that we understand how to write an inside and outside for a function that can be represented as a composition, even though it's not that way originally, we just say, hey, let's make it a composition. That leads us to the chain rule. The chain rule, this is used when a function can be considered as a composition. Key is finding the outside and insides, like above, given a function that could be represented as f of g of x. That is the key. So when you have a function that looks like a composition, so if I asked you to take the derivative of the square root of 2x plus 3, or if I asked you to take the derivative of any of these examples, it's not just a power rule, it's not a product rule, it's not a quotient rule necessarily. The D is a quotient rule, but it's also something else. A, you got the 2x plus 3 inside, so you'd think power rule. You got the square root, so you think power rule. But because one thing is inside of another thing, it complicates things, kind of like a product complicates things, kind of like a quotient complicates things. When you have this outside and inside stuff, you have to chain derivatives. You're going to be doing what's known as a derivative of the outside and a derivative of the inside. So I'll write this out in plain English. The derivative of a composition is the derivative of the outside times the derivative of the inside. That's the chain rule. But this is a math class, so you know we're going to write it as a formula. So here we go. d dx of something. And that something is a composition. Now, because I'm putting brackets for the derivative, I just double parentheses the composition. It's not a real big deal. So the derivative of the outside looks like this. F prime of g of x. And I am going to use brackets this time. Since you wouldn't have a double bracket. This is the derivative of the outside, then times the derivative of the inside. That is not the composition O, that is a shaded O. Composition O's are like an open circle. So again, this is the derivative of the outside, the F prime part. And times this is the derivative of the inside. Now, when you actually go to take the derivative of the outside, you are going to do this kind of red X thing. You're going to use that to represent it. But when you actually go and show the answer, you're going to have to go and write what the inside is. So when you go through and try to do derivatives this way, I guarantee that you'll get way more answers right if you write what the inside and the outside are, show the derivatives of each, and then plug them into the formula. It's right here. And you got to memorize this formula. Like I said, we get a decent amount of formulas to memorize in here. Only a third of what a regular calculus class gets, but we do have to memorize a decent amount of formulas. So far, we've got the limit definition of the derivative, which we kind of shy away from for a while. Then we got the power rule plus its two special cases. Then we got the product and quotient rule, and now we have our chain rule. So again, this right here is our chain rule. We're chaining derivatives. We're multiplying a derivative of an outside times a derivative of an inside. Derivative of the outside times the derivative of the inside. Derivative of the outside times the derivative of the inside. That's the way I think about it. So when I do examples, I write what the inside is, what the outside is, what the derivative of each of those is, and then multiply. And that's it. So let's try it out. Not with red ink though, with black ink. Example, what are we up to? 2. Find the derivative. Given for A, and we're going to have this be 2x plus 3 in parentheses raised to the, 2x plus 7. Not that it matters that much if I had it wrong, but let's be consistent, and then cubed. 2x plus 7 cubed. So I just wrote the function. I didn't write f of x equals for this one, so I could call them f of x and g of x for the outside and inside. But I will start writing these as f of x equals or y equals. So it's a lot better just to write out the words outside and inside. Okay, so there's our original function. This is a composition because you've got stuff inside and stuff outside. It's not just 2x cubed, it's 2x plus 7 in parentheses cubed. If you wanted to do this derivative without a chain rule, you would have to multiply all this out. You'd have to take 2x plus 7 times 2x plus 7 times 2x plus 7. You'd FOIL, then you'd multiply that 6 product, then you'd do your power rules. Well, unfortunately, that won't work for every type of problem. While you can do it for this one, you can't do that for a square root. It would be very, very, very difficult to do it with B. And again, C and D, you can't do it with. So we need to practice this idea of insides and outsides and then taking both derivatives. So the inside, I would call that the 2x plus 7. And again, I can call this the G if I want to, but I'm gonna avoid that. Then the outside, that would be the inside cube, but instead of writing the literal inside of 2x plus 7, that's where we replace what the inside function is with an x. That's showing that substitution. And then everything else, the parentheses cubed, but I don't really need the parentheses because now it's just x. So x cubed. I can wrap it in parentheses if I want, but it's unnecessary, so I don't. So that's our inside and outside. Now we need to take the derivatives of each of these things. So the inside derivative, that's me saying the derivative of the inside, or I could write d dx of inside. This would be another way, and I'm going to erase it in a second. I really wish my dog would stop barking. I don't know if y'all can hear that or not. So the derivative of the inside, well, the derivative of 2x is 2. Let me do this in blue. So the derivative of 2x is 2. That was a special case of the power rule. The derivative of 7 is 0. Again, special case of the power rule. Then the outside derivative this would be 3 times that x squared. And again, I'm going to leave that as a red x for now to show that that's a special variable that when we actually go to write the derivative, we're not going to be writing that red x. We're going to write what the inside is. So special memo. When you write the answer, the red x is really the inside, which in this case is 2x plus 7. Okay, so d dx of 2x plus 7 to the third power. We're finding the derivative, the slope function. And the chain rule is the derivative of the outside times the derivative of the inside. Here's the derivative of the outside, which is the 3x squared. But I'm doing something wrong intentionally. I'm doing something wrong intentionally. As I just said, when you go to write your derivative, that red x should not be an x anymore. This is wrong. This should not have been there. Instead of writing the red x's, we're supposed to write what the inside is, which is 2x plus 7. So that's what I'm supposed to write. So again, instead of the red x, and I'll still write it in red, I write parentheses 2x plus 7. I need a parentheses because the 3 is a multiplier. And then the exponent was the 2. So again, this right here, this 3, then the red ink and the exponent is this right here. That's the derivative of the outside. But you don't write x for the outside bit. You write what the inside was, because this is just a small representation of it. Not a small, a temporary representation of it. That's what I meant to say. A representation for a small time. Okay, so that's the derivative of the outside. Then we have our times. And this next part is supposed to be the derivative of the inside. Derivative of the outside times derivative of the inside. The derivative of the inside, we just had 2, so we just write a 2. That's the calculus part. We've done the calculus. The algebra is clean this up as much as you can. There's a 3 and a 2 that are outside that can be multiplied. So that gives us a 6. That was the 3 times the 2. But the 2x plus 7 squared, there's nothing really necessary there. So that's our answer. Now, sure, you could take the 2x plus 7 and multiply it by itself and FOIL it and then distribute the 6. But here's the thing. The original problem was written with a parentheses and an exponent. We tend to like our answers in a similar format. So I would say this is a better format than expanding everything with all that extra multiplication. I'm not saying it would be wrong. I'm just saying this is likely a better format. So that was the problem. We figured out what to call the inside and the outside. When we labeled the outside, we labeled the inside as that red X. Then we took the derivative of each of those things, which was this and this, and then the derivative of the original is just the product of the derivative of the inside and the outside, but that red X that was representing the inside must actually go back to being the inside. It's kind of like when you do a substitution, when you go from dollars to yen. I don't want an answer in yen, I want to answer in dollars, so you got to go back to the dollar. And in fact, a couple of the homework problems actually take you through this process using a substitution instead. So I'll show you what I mean by that a little later, but for now, let's not throw too many methods at you all at once. Let's practice this method again. B. And let's have this one as y equals 5 parentheses 3x squared plus 2x minus 6. Close it and then raise it to the 9th power. Okay. So because we got stuff inside of other stuff, this is a composition. This is our chicken cordon bleu. It's best to label what the inside and the outside are. And then ultimately taking their derivatives. The inside is generally the inside of something. It's almost painfully obvious most times, but there's problems where it's not. It's going to be the 3x squared plus 2x minus 6. Which makes the outside everything else, but wherever you had the inside written, you're now just going to write it as an x. I like to have that color for emphasis, so it should be 5 times our x to the 9th power. I like the red for emphasis again. So the outside function, we're just calling 5x in the ninth, but I'm using the color to denote, hey, that red is really supposed to be something else in the long run. Now we should do each of these derivatives. I'll do them in blue. The derivative of the inside, well, the derivative of 3x squared is going to end up being 6x. You take the 2 out front, you multiply it by the 3. 2 times 3 is 6. You decrease the exponent by 1, and that gives you x to the first. You should all already be masters of the power rule. I can't emphasize that enough. Plus the derivative of 2x. And if you're not, go and do 2,000 of these. This is one of the special cases. The derivative of a linear term is just the coefficient, so that's a 2. Special case here as well, the derivative of a constant is 0. So the derivative of 3x squared plus 2x is 6x plus 2. For 5x to the ninth, its derivative, you'll bring the 9 out front and multiply. 9 times 5 is 45. And then we have our special red x, and it'll be raised to the 8th power. And again, when we're talking about the x, the outside function, that x really represents something else. So that derivative is 45x to the 8th. So the derivative of this thing, which because it's y, we can call it y prime, or we can call it dy over dx. It's the derivative of the inside, which is nice and normal, 6x plus 2. But we got to multiply this by something, so we should probably wrap it in parentheses, times the derivative of the inside. I'm sorry, outside. We just did the derivative of the inside. Pardon my misleading. So the derivative of the inside times the derivative of the outside. The derivative of the outside is this 45x to the 8th. So times 45, but not x to the 8th. This is wrong, this is wrong, this is wrong, this is wrong. Remember that in the outer function, the x represents the inner function. So that's supposed to be 3x squared plus 2x minus 6. That's what the x really represents. And then that's raised to the 8th power. And then this can be cleaned up. Now, this part being raised to the 8th power would be unseemly to have to multiply out. We generally are not going to do that. This is the point of the chain rule, so you don't have to do all these big products. However, this linear 6x plus 2 without an exponent is 45. That can be multiplied together, or you could leave them separated. The best thing to do is probably just leave the 45 in front. So very often you'll see it done this way: 45 times 6x plus 2 times the 3x squared plus 2x minus 6, and then raised to the 8th power. That is one acceptable answer. Oh, my cough made me mess up. But there are alternative answers. Your y prime. Because the 6 and the 2 have a common factor of 2, you could actually take that out and make this 90 times 3x plus 1 times that other parentheses, 3x squared plus 2x minus 6 to the 8th power. So again, what I did was I took a GCF of 2 out of the 6 and the 2 here. Because there's a GCF in these two, I can take it out because there's no exponent. I couldn't do that with the thing with an exponent. And 2 times 45 is 90. Or another alternative, if you distributed the 45 times 6, what's that, 270x plus 45 times 2 is 90. Now there's no number in front of the parentheses, it's been distributed in, and then the 3x squared plus 2x minus 6 raised to the 8th power. All 3 of those are acceptable answers, and my math lab should take all 3, and I would take all 3 on a test. Sometimes it's best to have the most factored version, which is the bottom left. This is the most factored. I would argue in many instances this is the best version, but really the one that I have boxed up, because taking out the extra factor of 2 generally doesn't do anything constructive. I'd say that one was just as good. I would say my least favorite's the bottom right. I would say this is my least favorite. But again, that doesn't mean it's wrong. It just means I like it less. And opinions are subjective, right? Is that it for that page? Yes, it is. All right, so let's do another one. See? And we'll actually write this one as f of x equals, so we definitely don't want to write the insides as f's and g's. So this is going to be 3 over the square root of 5x plus 9. Now, I see a square root, I see something in a bottom. There's a lot of things that are going to have to be cleaned up with this. So the inside function, there's a world where it could be the entire square root in the bottom, but it's not. It's just the inside of that square root. It's the 5x plus the 9. Making the outside function everything else, but when you go to write the inside function, just write it as an x. So 3 over square root of x, which represents the inside. Now, when we go to take the derivative of the outside, this is not in a good format. We need to clean this up. So that's 3 over x to the 1/2. This is going to get tedious. Which is 3 times x to the negative 1/2. This is the format we need to be able to take the derivative of the outside. Sorry, my dog's distracting me barking again. Sometimes I can talk over them, sometimes I can't. I'm easy to distract. So we needed this square root in a bottom, in the top, and with the rational exponent so that we can apply the power rule. We can't just take the derivative of 3 over square root of x unless you've memorized it, which admittedly I have, but I've done this 10 million times. All right, so now let's do the actual derivatives. The inside derivative of 5x would be 5. And the derivative of 9 would be 0. The outside's derivative, and again, we'll keep that x red to represent the inside the whole time. We bring the negative 1/2 out front. So that's 3 times negative 1/2. You could put the negative 1/2 in front if you wanted. And then there's our red x, representing the inside. And we're going to decrease its exponent by 1. And I've shown this before, negative 1/2 minus 1 is negative 3/2. I'll write that really, really quickly, and then I'm going to erase it because I don't want too much stuff jumbling up. Negative 1/2 minus 1 is negative 1/2 minus 2 over 2, which is negative 3/2. That's where that came from. LCDs, if you can't do that in here, I don't know how you're in calculus. Okay. Now, the original function was written with square roots and bottoms, so it's probably okay to go back to that type of notation. So that's what we'll ultimately do. You can do it now or you can do it later. Let's wait till later just to see both types of answers. So I'll hold on to switching this to the bottom and changing it back to a radical form. But now we can say that our derivative, f prime of x, or df dx, however you wish to write it, it's the derivative of the inside times the derivative of the outside. Well, and by the way, that -3/2, I should have cleaned that up. Darn it, that's -3/2 times x to the -3/2. Come on. Ugh, time consuming. Okay, derivative of the inside, that's the 5, times derivative of the outside, that's all of this. So times -3/2, then our special x, which really represents the inside being the 5x plus 9. So that's another parentheses, 5x plus 9, then that thing is raised to the -3/2. Well, the 5 times the -3 is a -15, so this is -15/2, and I can get rid of the blue parentheses. Then times the 5x plus 9, raised to the -3/2. Analytically, that answer is correct, but no one likes it in that format. We want to bring the negative exponent down to the bottom. So this will be -15 over 2 times parentheses 5x plus 9 raised to the +3/2. And then we want to switch to the radical notation, which gives us -15 over 2. The bottom of that exponent's a 2, so it's a square root, big old square root. The exponent's a 3, so that's the power. So inside we got a 5x plus 9 in parentheses raised to the 3rd. This is our derivative, and that's all we can do with it. It's technically not in an okay format because there's a square root in the bottom, but again, our class does not focus on that. This is okay to put in my math lab. It might even be okay with the rational exponents. I'm not saying, because I've seen my math lab accept a lot of answers, as well as turn down some answers I didn't expect. Practice makes perfect. But the moving of the -3/2 as an exponent down to the bottom and then changing to a radical, you could have done that up here. So the outside part, just note that that would have been, I don't want to write it there, I want to write it below. Note the outside derivative, if you had simplified, you would have gone from -3 over 2, then the red x to the -3/2. I'm going to skip the color changing for now. That would be -3 over 2 x to the +3/2, which would be -3 over 2 square root of x cubed. And that x would be red. I'll make them all red now. And you can see that the -3 is in here before we multiplied by the 5. The 2's in the bottom, square root's in the bottom, and there's the inside cubed. So it did not matter when we simplified the rational exponent with its negative and all that jazz. We could have done it while we were describing the derivative of the outside, or we could have done it when we did the derivative of everything as a whole. Okay, so let's try another one. Do I have enough space? Yes, I do. Wrong color. Sorry, I'm just looking at something. I was trying to decide if I could make this one blue. Let me try that. Ooh, that looks really ugly. So yeah, I didn't think that would work. I'm just gonna have to keep switching colors. All right, D, f of x equals, silly me, f of x equals x to the 5th plus parentheses 1 minus x raised to the 5th power. This is where things start getting a little more interesting. So we're definitely going to step it up with the next couple of problems. And E is going to be even harder. F, you could argue is even harder, but I think E is probably the hardest one we'll do. This one is unique to the previous three because we're going to have to do the inside-outside stuff on the 1 minus x part, but not, but not on the x to the fifth. So this is a very unique type of function where you've got parts that you don't have to do the inside-outside with because this part is just a normal derivative, but then this part you do. So we don't worry about the in and out on the x to the fifth part, just the parentheses 1 minus x to the fifth part. So the way I'm going to write this out is that f prime of x is going to be the derivative of the thing on the right side, x to the fifth plus the parentheses 1 minus x to the fifth. I'm just taking expanded notation here because I know how to do the derivative of the x to the fifth. It's 5 times x to the fourth. So in blue, I'll show that derivative. It's 5. Wrong thing. The fact that I made that blue is making me want to click it now. Let's put it back to gray. Blue. So 5x to the fourth. That was this part. That's a normal derivative, no chaining necessary, no product, no quotient, just normal old power rule. But we can't do that for the other part, the d dx of the 1 minus x to the fifth. I haven't taken that derivative yet because we need to chain this part. We didn't have to chain the x to the fifth, so we took its derivative. We do have to chain the next part, so that's what we're going to focus on. That 5x to the fourth you're going to see in the final answer, it's just going to come back. But for the rest of this problem, when I'm doing insides and outsides, you're not going to see this guy anymore. I'm not completely erasing, I'm just saying that 5x to the fourth we're pausing on. So focusing on this, only focusing on this. The inside would be the 1 minus x, and the outside would be our x to the fifth, but we're going to use a red x instead to represent the inside. It's the inside to the fifth power. Then we can go and do their derivatives. The derivative of 1 is 0 because it's a constant. The derivative of negative x, there's a negative 1 implied to be there. And that's a linear term, so its derivative is the coefficient, which is negative 1. So the derivative of the inside is just the negative 1 because this thing has a slope of negative 1. For the outside part, its derivative would be 5x to the fourth. Drop the coefficient down, decrease the exponent by 1. So 5x to the fourth, but again, I'm still going to use that red x just for visual flair, saying that, hey, this is going to represent the inside function. Now we have the derivative of the inside and the outside. We can do our chain rule now. So f prime of x, the derivative of the original function. Now we can't forget this. A lot of students end up forgetting the blue 5x to the fourth. Remember the derivative, we were doing the derivative of the x to the fifth, which was this thing, no chaining necessary, so here it is. Then we have our plus. Now this next bit will be the derivative of what we did have to chain. So the derivative of the inside times the derivative of the outside, where the red x really is the inside. So plus negative 1, that's the derivative of the inside, times the derivative of the outside, that's the 5, then our x is really 1 minus x. Again, this x, we now write what the inside is. When you go to write the actual derivative, write what the actual inside is. and that was supposed to be the fourth power. This can definitely be cleaned up. The 5x to the fourth in the front is just 5x to the fourth. The negative 1 times the 5 is a minus 5. And then you got your parentheses 1 minus x to the fourth power. That's all we really need to do. You could say, oh, there's a GCF of 5 between these two terms and pop it out. It doesn't really have a good effect, though. The only real okay alternative answer, which I just described, would be popping a 5 out of both of these terms and then having a bracket x to the fourth minus parentheses 1 minus x raised to the fourth. And I'll write that as df dx. Remember, f prime is df dx. It's the same thing. They're both acceptable answers. My math lab should take either of those. My personal opinion is that the top one is better. But again, that's an opinion. Opinions have a lot of variability. So this problem was unique to the previous three in that you didn't have to chain everything. There was just some pluses or minus, some terms that had simple things that didn't need an inside and outside. X to the fifth, power rule's okay. 1 minus x in parentheses raised to the fifth, you got to chain it because it's got an inside and an outside. The inside here is just x, so that's fine. All right, so let's step this up even more. I'm going to go ahead to the next page because I'm going to run out of room. I know I will. E. Let's now do f of x equals bracket parentheses x squared plus 1, close it, cube it, then a plus x, then close the bracket, and have that be to the third power. Okay. This is, in my opinion, the most complicated chain rule we'll do all day. Again, some people might argue that the next two, one of them could be more complicated by mixing a product in a chain rule or a quotient in a chain rule, but I really do feel like when it comes time to test, if I threw all 7 of these problems on the test, people could knock out the first 4, almost no one would get this one right, and more people would get the next 2 right. Well, there's definitely a chain rule going on. We've got this whole thing raised to a q power. But there's another problem going on here. It's bigger than that. So this right here is an inside, but also on the inside, there's another inside. There's another complication. You've got parentheses inside of parentheses. This is kind of like Inception. We've got nested compositions here. We put some cheese, wrap that up inside of the ham, then we wrap that up inside of the chicken instead of just putting the cheese and ham inside of the chicken. So we put one thing inside of another thing inside of another thing. This is our turducken, our chicken inside of a turkey inside of a duck, or whatever the order is supposed to be. So this is a nested composition, which means we will need to chain this twice. So for the first layer, the first dive into the dream, I would call the inside everything inside of the bracket. The x squared plus 1 cubed plus x, and then I'd call the outside everything inside of the bracket cubed, the red x representing everything inside of the bracket. Now when we go to do the derivatives of these, when you go to take the derivative of the inside, you will need to chain this part. but then there's a plus, and the derivative of this x is a 1. So again, where I have chain and exclamation mark, I'm referring to this. We're going to have to do another inside and outside on that, but we're going to do that in a few minutes. So again, the part that's underlined will need to chain. So you're chaining a chain. It's like an f of g of h. There's an h function inside of a g function inside of an f function. For the derivative of the outside, though, everything's normal, thankfully. Drop the 3 out front, decrease the exponent by 1. I'm keeping my red x for emphasis that should be the original inside. So again, I'm even going to make a note here that this red x represents the original inside, which was the x squared plus 1 cubed, then plus another x. That's what that red x represents. And I want to change the color so it doesn't get too confusing. It feels weird saying x equals this thing because that can't be true, right? X can't be something more than x. But again, it's just showing a substitution that happens later. I also did not write the derivative for the outside part here. I wrote outside, not outside derivative. Make sure you write your derivatives. Outside is black, the blue is the outside derivative. So for now, we're going to pause. For now, f prime of x is going to be the derivative of the inside times the derivative of the outside. Well, the derivative of the inside is this thing that we don't know. It's whatever we have to chain plus the 1. So that's the derivative of the inside times the derivative of the outside. That's the 3. And then the x, which it represents, is this thing. X squared plus 1 cubed plus x. And that's supposed to be squared. So right now what we have is the derivative equals this thing, but there's an unknown here. We don't know what the derivative of the inside is. We haven't done it yet, so let's do that now. So let's pick a different color. Let's go with green. Let's find d dx of what we said we have to chain, the x squared plus 1 cubed. So for this one, we're going to call the inside the x squared plus 1, and its outside would be the inside cubed. If you don't like using x to represent that, you could also write the words in cubed, and then in the final thing, instead of writing in, write what the inside is. And by in, I mean the word in, not the letter in. So again, for emphasis, let's pick another color besides red. Let's go with pink. Close enough. So the outside is really that thing cubed. So now this feels like a whole new problem. We're doing this derivative. Here's its inside, here's its outside. Now let's do the derivatives of each of those. I'm going to stick with the green just because I've already got too many colors going around. The derivative of the inside would be 2x. The derivative of x squared, you bring the 2 down, and then you decrease the exponent by 1. I wonder if y'all can hear my dog panting. Dogs are fun. And then the derivative of 1 is 0. Then for the outside, the derivative of x cubed, you bring the 3 out front. And then that x is now going to be squared, but we'll stick with the hot pink to represent its inside function. So again, please note that the hot pink x is really representing the inside function, which was the x squared plus 1. So every time I write that hot pink, that's really what it is. Okay. So that says the derivative of the inner thing we had to chain is going to be the derivative of its inside, which is 2x, times the derivative of its outside, which is the 3x squared, but again, the magenta is really x squared plus 1. or the pink, whatever you want to call that color. And that's squared. The one thing we can do with this that's easy is the 2x times the 3 is 6x. So 6x times x squared plus 1 squared. This right here is what gets plugged in. All this is going to get erased in just a second. Here, where it says chain exclamation mark. Because again, we didn't know that derivative initially, we had to chain it. Now that we have chained it, we can go back and fill it in. So we finally have f prime of x equals, we got the parentheses, the thing we got from chaining, which is this, the 6x squared times x squared plus 1 squared. I'm sorry, that's not 6x squared. 6x times the x squared plus 1 squared. So we have our parentheses, the thing we got from chaining, which was all this green, but then there's the plus 1 that was after that. This plus 1 is this plus 1 right here. Then we're going to close that parentheses. You could have made this outer parentheses bracket now if you wanted to. That would have been perfectly fine. Then the times 3 bracket parentheses x squared plus 1 cubed, then a plus x, and then all squared. Now, believe it or not, this is really all you can do with this. Again, I personally like this as a bracket instead of a parentheses. But it's this thing times this thing. There's no factors anywhere. There's definitely not any factors anywhere. So f prime of x, the only thing I want to clean up is this 3. Nobody wants a constant in the middle of two products. Put the 3 up front. So 3, bracket, then the 6x, then the parentheses, x squared plus 1, and then squared, and then another plus 1. Close the bracket. Then the other bracket, parentheses, x squared plus 1 cubed plus x. Close the bracket and square it. This is the answer. You might think that x squared plus 1 is a GCF. Well, it's here and here, but it's not next to this 1, it's not next to this x, and it complicates things because there's an exponent of 2 here as well. There is really nothing you can do here except multiply everything else together, which would be nightmare fuel. So we don't ask you to do that. Again, it is my personal opinion that that's the hardest problem in the section. I'm not saying it's the hardest, I'm saying my opinion is it's the hardest. Box it up. The reason it's the hardest is because of the inception thing going on. So we had the main inside, but that inside needed an inside and outside as well because it was a composition in part of it. So when we went to take a derivative, we were going to have to chain that, which we did in green below. The outside derivative was pretty normal. Outside derivatives are generally pretty normal because you end up boiling them down to just like a number times a variable with an exponent. That's the whole point. Your outside derivative should always be something clean and simple like this. You have to be very careful when you have parts that need to be chained and parts that don't. It's very easy to miss this plus 1. I will admit, when I taught this class, I want to say 2 or 3 years ago, I specifically remember this problem using it and forgetting my plus 1 in the answer. And then I went back and looked at my notes and I went, oh, darn it, I need to emphasize that to the students. I will never forget making that mistake. So again, there's a decent amount of algebra to keep up with this stuff. The calculus was really just a formula applied a couple of times. The algebra was understanding compositions. The algebra was understanding how to simplify things. The calculus was drop exponents down, label an inside and an outside. All right, that was E. Let's move on to F. Let's have this function be, why am I on red? Because that was the last thing I clicked, obviously. F of x is 2x plus 3 times 4x minus 7, but that one's squared. This is a product, so we'll need the product rule. One of the products has an inside and an outside, so we're going to need the chain rule. So this is both a product and a chain rule. The last one was chaining a chain, this one's product and chain. Spoilers, the one we'll do after this is the chain and the quotient rule. We're going to try all the different combinations. So we will need the chain and product rule. And I'm going to write the product rule that the derivative of some f times g, a first times a second thing. I'm going to write this the way I like to do things that's consistent with the quotient rule. I always go the second times the derivative of the first plus the first times the derivative of the second. This is the way I will always do my product rules moving forward. It's just my particular habit. As I've said, there's at least 8 different ways to do a product rule and get it right. The quotient rule, there's only like 2 or 3 ways to do it and get it right. There's less options because of the minus instead of the plus between them. Okay, so f prime of x. And I'll use these as first and second. It's going to be the second thing times the derivative of the first. So I'm calling the first bit the 2x plus 3, and I'm calling the second bit the 4x minus 7 squared. So my f is first, my g is second. If you want to go ahead and label out those derivatives, you can. Sorry for my coughing. Eraser. I want some more room here. I don't want to do that yet. I could have, but it's fine. So let me go ahead and show what these derivatives are. The derivative of the first, the derivative of 2x is 2. The derivative of 3 is 0. So that's the derivative of the first. And the derivative of the second, well, we're going to have to chain because of the inside and the outside. So I'll hold on to that for a minute. I don't want to chain it yet. I just want to show what our derivative looks like initially. So f prime of x for now, it's the second thing times the derivative of the first. So the second thing is the parentheses with the 4x minus 7 squared. So here's the second times the derivative of the first. So we're multiplying these two things, which is 2. Then plus the first, which is 2x plus 3, times the derivative of the second, which we don't know yet. We said we'll need to chain it. So maybe you write question mark, question mark, question mark, but I'm going to be a little more specific than that. This should be times the derivative of the 4x minus 7 squared. Darn my cough. And I think I tried to cough earlier. I tried to mute and then cough, and it's making me hit the button twice. So I may have coughed for y'all really loudly and then muted myself, but I saw it quickly and unmuted. So sorry if I coughed really loudly earlier. I feel it coming on. I try and avoid it. Anyways, so again, right here, all we've done so far is emphasize the product rule. second times the derivative of the first plus the first times the derivative of the second. Again, the order of this is very, very, very open as long as you have a derivative times a regular function of the other thing. So the 2 in the parentheses 4x minus 7 squared could be last. I can put the 2 in front. I could put it after. I could put this parentheses after the derivative before. Like I said, 8, arguably 16 different ways this could be written out and be accurate. But now let's find out what this is. Now let's do the chain. So let's just focus on d dx of the 4x minus 7 squared. So we're going to need outsides and insides. The inside is the 4x minus 7. The outside is the inside being squared. The inside I represent with the x, the red x. You could write in squared if you prefer that notation. It's up to you. Doing these derivatives, the derivative of the inside is just 4. The derivative of 4x is 4. The derivative of 7 is 0. The derivative of the outside, you bring the 2 out front, decrease its exponent by 1, so it's 2x to the first power. I'll write the 1 for emphasis in the fancy 1 language. But again, you really don't write that 1 ever. So remember that red x is really the inside, which is 4x minus 7. That's what it represents. It's extremely important to remember not to write that as an x in the answer. So that 2x plus 3 that was in parentheses times the derivative, we can now do the derivative. This derivative would be the derivative of the inside times the derivative of the outside. So the derivative of the 4x minus 7 all squared is the derivative of the inside, which is the 4 right here, times the derivative of the outside, which is 2x, but don't write x, write the inside, which was 4x minus 7. Again, the 4 is the derivative of the inside. The 2 in the red ink is the derivative of the outside, but don't write x for the outside, write what it actually represents. And this, of course, can be simplified to 8 times 4x minus 7. Now, as you do these more and more, you may get to the point where you don't need to write what the inside and the outside are. You get more of a flow with this. You just kind of learn to take the exponent, drop it in front, leave the inside alone, and decrease the exponent of the inside by 1. Something like that. So finally, f prime of x. This 8 blah, 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 blah is this thing right here. Now we're able to finally have the derivative completed. So that derivative originally was, and I don't want to reorder things so you don't get confused, 4x minus 7 squared times the 2. That was the second times the derivative of the first, plus, here's the first, 2x plus 3, times the derivative of the second. So that's times what we just got of 8 times 4x minus 7. Clean it up. Put constants in front. So the 2 needs to go in front. So 2 parentheses 4x minus 7 squared. Then plus 8. Put it in front. 8. And make sure you close the parentheses in front of or after the 7. So 8 parentheses 2x plus 3 times 4x minus 7. Now, maybe you can stop here. Honestly, no, this is not good enough. This is simplifiable. And you might say, well, man, that's a lot of different mess going on. Why is this simplifiable? Because look here, this factor, this term has 4x minus 7 as a factor. This term with the 8 has 4x minus 7 as a factor. There is a GCF this time. And I mentioned in the previous example, it felt like there might be, because you got this x squared plus 1 here and here, but it's not everywhere inside of the bracket. It's not everywhere inside of this bracket. So that wasn't a GCF, but this time it is. So usually what happens if we take GCFs out, we can make cleaner looking answers. This is not a very clean looking answer, and we can make it clean. So there's a GCF of parentheses 4x minus 7. It's here, there's 2 of them, but we're only going to take 1, and then it's here, there's 1, and we're going to take all of them. So let's take the GCF out. We're taking out the 4x minus 7. So we're taking this out, and we're going to open a bracket or a parentheses. There's a lot of parentheses, so probably a bracket. So we're taking one of these away from the thing with a 2 and the thing with an 8. There were 2 of them in the first term, which means now there's one of them left. So there's a 2, then a parentheses, and the 4x minus 7. So that was me taking the GCF from this bit. I haven't gotten to the 8 yet. Then there's the plus 8. The 2x plus 3 is still there. I'm not taking that away. I'm taking the 4x minus 7 away. So if I had 1 and I take it away, there's none left over. So this is taking a GCF out. The red parentheses will represent the GCF here. If you were to distribute this parentheses times 2 in that parentheses, you get a second one. Times the 8 in this parentheses, you'll get the 2 unique parentheses. Now what you can do is clean up the inside. And I'll put parentheses S there saying sometimes it's both insides, but really it's just the inside of the bracket. We can distribute the 2 and the 8 because nothing can happen inside of the red one. It's just 4x minus 7. So bracket 2 times 4x is 8x. 2 times negative 7 is negative 14. 8 times 2x is a plus 16x. 8 times 3 is a plus 24. Combine like terms. And we get f prime of x is 4x minus 7 times, and I really don't need that as a bracket, so I'll go back to a parentheses. 8x plus 16x is 24x. And then negative 14 plus 24 is a plus 10. This is a much prettier version of the answer. Generally speaking, when you have product and chain rules together, this happens, where you end up having a GCF that's like a binomial or something, and then you can clean up and clean up. Note that there is a GCF of 2 as well in the second parentheses. The 24 and the 10 have 2 in common. So really, you could take this one step further. If you prefer this to be as factored as possible, you'd have 2 times 4x minus 7. Now I'm taking the 2 from the second parentheses, not the 4x minus 7, so that's why I didn't change it. 24 divided by 2 is 12, so that's a 12x. 10 divided by 2 is 5, that's a plus 5. Both of these are good answers. I don't really think one's better than the other. I personally prefer the second version, but there's nothing wrong with the first version. It's more about preference. But if you had stopped way up here, this would not have been an acceptable answer on a test. Homework, it likely wouldn't take it either. It would say, well, while this is analytically correct, there is some simplifying you can do. Sometimes you get ugly answers because there's no GCFs, there's no fancy algebra you can do. Sometimes you get to a point you think you have an answer, but because there's stuff in common or like terms, blah, 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 then you can take it one step further, and you should in those instances. So that problem had a decent amount of complexity to it, but I still think chaining a chain is more complex. Opinions will vary. Now again, the problems that I do in lecture, these are comparable to what you'd expect to see on a test, and I'm trying to make sure that the homework problems line up pretty well as well. And by the way, in this homework, if you already did a couple problems, one of you is a real go-getter at least. The last like 5 or 6 problems I gave as freebies because they were kind of extended concepts, more complicated, whatever, you know. All right, so one more of these. We did the product in the chain, now let's do the quotient in the chain. So f of x equals, and this is x plus 1 over x minus 1 cubed. Now, you could have a product that needs to be chained, or you could have a chain that needs to have a product rule done. The last one was one way. It could have been done the other way. This is kind of like the other way, where the quotient is inside of the chain rule. Last time, the chain rule was not inside of the product. It was part of one of the factors. What I'm saying is, you could have also had a problem that was something like x plus 3 times x minus 7, and then this whole thing is raised to the, I don't know, 10th power. That would be chaining a product instead of a product and chain. Okay. So this is a quotient rule. One more reminder for the quotient rule. If you had f over g, instead of calling them first and second, it goes the second times the derivative of the first minus the first times the derivative of the second, all over the second squared. All right, so this is just one big inside and outside, so we're going to chain this at first. We would call the inside the x plus 1 over the x minus 1, and that makes the outside everything cubed. So red x representing the inside, and then cubed. So then remember, if you need to make a note of this, your little red x really represents the x plus 1 over x minus 1. Make sure you're not writing that x in the derivative in the final answer. It should be x plus 1 over x minus 1. All right, so our derivative of the inside, we're going to need the quotient rule. I'm going to need more space. I'm just going to write that there for now. That's the inside derivative. Make sure you don't write inside a second time. And then the outside derivative would be 3x squared with a red x. All right, so let's focus on the derivative of the inside. I'd call the top x plus 1 and the bottom x minus 1. Taking these derivatives, the top derivative would just be a 1 because the derivative of x is 1, the derivative of 1 is nothing. The derivative of the bottom function is also 1. It's actually quite simple. So the derivative of the x plus 1 over x minus 1. That's the derivative of the inside. Using the formula, it's the bottom times the derivative of the top. The derivative of the top must be in the first term. You could put the derivative of the top before the bottom, or the bottom before the derivative of the top. But you can't have either the g or the f prime, top or bottom, respectively, be after the minus. These two things have to go before the minus. So going in the order, g means bottom. So the bottom is the x minus 1 times the derivative of the top, which is 1. So don't really need that parentheses because of that, because it's just x minus 1, but I want to be thorough. Then the minus from the formula, not a plus, a minus. And then it's top times derivative of the bottom. The top is the x plus 1, and we'll multiply that by the derivative of the bottom, which was 1. Remember, the quotient and the product rule, you end up using all 4 of these bits. Quotient rule, you also have that over the bottom squared, the bottom being x minus 1, so it's x minus 1 squared. We can clean this up, though. Distributing a 1 does nothing, so that's x minus 1 minus parentheses x plus 1 over x minus 1 squared. Distribute the negative, so that's x minus 1 minus x minus 1 all over parentheses x minus 1 squared. Combine like terms. X minus x cancels. Negative 1 minus 1 does not cancel. It makes negative 2. So negative 2 over x minus 1 squared. That is the derivative of the inside. Now we know the derivative of the inside and the outside, so we can do the chain. So f prime of x, or df dx, whichever way you like to write it. It's the derivative of the inside times the derivative of the outside. This is the derivative of the inside. This is the derivative of the outside, but remember, that's a special x that really represents the inside itself. So, derivative of the inside was the -2 times x minus 1 squared in the bottom. So that's the derivative of the inside, times the derivative of the outside, which is this thing, so that's times 3, and then the x, which really represents the fraction, x plus 1 over x minus 1, and then you're squaring it. Derivative of the inside, word for word, is right here. Again, this thing is the derivative of the inside. Part with the 3, this was the derivative of the outside, but making sure that you write the inner function where that x is, because that's what it really represents. All right, well, we got tops and bottoms that we can all put together. The -2 times the 3 is going to make a -6. Then you got an x plus 1 squared in the top. I'm just going to separate this as x plus 1 squared over x minus 1 squared. Then all over. There's your x minus 1 squared from the under the 2. And then here is the x minus 1 squared, and I'll show it in red. In the bottom, I just split up this thing being squared, the top squared over the bottom squared. The reason I did this is because now in the bottom you got x minus 1 squared times x minus 1 squared. You can stack the exponents. 2 plus 2 is 4. So ultimately this is -6 times x plus 1 squared all over x minus 1 to the 4th power. This is our f prime of x. What I think is interesting is this originally was all being cubed. The thing that was in the top dropped its exponent by 1. The thing that was in the bottom actually increased its exponent by 1. That goes in line with the power rule. But there are more complexities here because of the number. This 3 ends up bringing a 6 out front ultimately somehow. If these had been like a 2x plus 1 or a 7x minus 1, there would be extra multipliers in certain places because the derivatives of the top and the bottom would be numbers like a 5 or a 7 or whatever numbers I just said. But the basic core of the function, the basic idea is still kind of like, all right, if you just had the x plus 1, that would go from a cube to a squared. And if you had an x in the bottom being cubed, because of the way the algebra works, as we've seen, is the -3 turns into a -4, which is why the 4 goes in the bottom. So at least this part, the 2 parentheses, makes sense if you break it down that way. But the other numbers that come into play in and around this thing, you're never going to be able to predict just based on patterns. You have to do all this legwork. Okay, so let us show you that other notation that we mentioned, the other ways that the homework will do it occasionally. It mixes and matches. So the other notation is that you instead say that y is a function of u. You actually show the substitution like you would have done in pre-calc, taking like a x to the 4th equation and boiling it down to an x squared, where you say let u equals this, u squared is this. It's kind of like that. So you have your original function y, and you're going to make it a function of u, where u is a function of x. So this is still showing a composition. Here's your f and your g. But now you actually show, instead of a red x, you use the letter u, so it's a different independent variable. It makes it a little more clear for some people, but not everyone. So when you do it this way, f prime of u, also known as dy dx, because your original function was in x, but now we're just showing it in u, is going to be dy du times du dx. This is still the chain rule. It's written in an opposite order though. The du dx, this part is the derivative of the inside times the dy du, that's your outer function. That's the derivative of the outside. So this is still the derivative of the inside times the derivative of the outside, but it introduces a fascinating algebraic concept into calculus that shouldn't work, but it does. All right, your original function was in terms of x. So you had y equals x squared plus x to the fifth minus parentheses, blah, 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 blah. So you were originally trying to find dy dx because you had y and your independent variable is x. But there were some complexities in the middle that required this little substitution, this which is the same thing as us calling an inside and an outside. Look at this. You got dy and you got dx. You still have this dy and this dx are here and here. But then for the dy part, you put it over du, and the part that has the dx, you put a du above it. I know every single one of you are looking at this and saying, oh, there's a du in a top and a du in a bottom. These cancel and just make dy dx. Calculus doesn't work that way. They don't actually cancel that way. It is a necessary evil to have it written that way. And that is exactly what the chain rule demonstrates. But what it does is it gives you a way to chain anything, whether it needs to be or not. If I had some function of z, and I wanted to take the derivative of x, maybe x was dependent on the variable u, and the variable u was dependent on the variable v. As long as I kind of have a du and a du in the top and a bottom of different ones and just make them cancel, if they were going to cancel, I get back to the original thing. So I could do dz du times du dv, because u is dependent on v, I'd have to take that type of derivative for it. But v is dependent on x, so dv dx. It feels like algebraically the du's would cancel, the dv's would cancel, and you get the original derivative we were looking for. But again, this canceling doesn't really happen. It just feels like it would. Now, if this was a traditional calculus class, we'd be diving further into this idea. We're a business applied calculus class, so we don't. But I just at least want to take the very first example we did and show you how it could be done written with u's instead of the way I did it. And also, I like to actually write my chain rule a different way. I don't need to scroll up to see it. I've got it on my paper notes. I just got to find the page. Not that one. It was the 2x plus 7 cubed. So back to 2x plus 7 cubed. I'd say let u equal 2x plus 7. So f of u would now just be u cubed. That's the inside, that's the outside. Same concept, but now instead of using that fancy red X, it's a literal different letter, a u. So the derivative of this, if I say this is y equals, y prime is now the derivative of the outside times the derivative of the inside. Du dx is the same as u prime. Well, the derivative of the outside is 3 times u squared times the derivative of the inside is just a 2. Again, 3 in front. That's it. So the 3u squared, the derivative of the inside is just 2 because the derivative of 2x is 2, the derivative of 7 is 0. But we want our derivative to not have u in the answer. So we go back to our substitution. Well, u was 2x plus 7. So this is 3 times 2x plus 7 squared times the 2, which is really 6. And I could have multiplied the 3 and the 2 first to go ahead and get the 6. So 6 times the parentheses, 2x plus 7 squared. And that should be the same answer that we got originally, right? Yes, it is. It is correct. Honestly, this is a quicker way. This is the way I hope some of you pick up and do it ultimately, but I feel like as we start this idea, it's important to label things a little more methodically as insides and outsides. U is representing the inside, and then your function replaced with U is representing the outside. But again, in the final answer, you can't have U's, so it definitely just emphasizes the fact that you got to plug it in. You won't make that mistake with the red X still just being an X. All right, we got enough time to do one last example, and we'll call it a day. And let's go back to the tangent line stuff. For example 3, yay, we're going to find the equation of a tangent line to f of x equals 2 parentheses 5x minus 8 cubed at x equals 2. So we got a function, we got a x coordinate. We want to find the equation of the tangent line, which means we need the point and the slope. Well, the point would be very easy to figure out, f of 2. That's 2 times 5 times 2 minus 8 all cubed, which is 10 minus 8, which is 2, so that's 2 times 2 cubed, which is 2 to the 4th, and that's 16. So our point is 2 comma 16. That's half of what we need for the equation of the line, but it's the easy half. Now we need the slope. To find the slope, we got to do f prime. We got to do the derivative. Well, unfortunately, we're going to need to chain rule this. And I'm going to practice this doing the u stuff. Since I only did it once, let's do it one more time just to mix things up. If you need to write inside is 5x minus 8, outside would be 2 times a red x cubed, and then do those derivatives independently, that's fine as well. I'm just going to show you the other way. So we let u be the inside, which is the 5x minus 8. So that's what we call the inside. Then the outside part is now f of u being 2 times u cubed. That's what we call the outside. And then our derivative, f prime of x, would be the derivative in terms of u times the derivative of u. So f prime of x, the derivative of the function in terms of u, that's the derivative of the outside, would be 2 times 3 times u squared. Bring the 3 out front, drop the exponent by 1. So that's the derivative of the outside, times the derivative of the inside. The derivative of the inside would be 5. If you need to see that, inside derivative is 5. Outside derivative would be 3 times 2u squared. So times the derivative of the inside, that's the 5. Well, 2 times 3 times 5, you can clean up all of that, right? 2 times 3 is 6, 6 times 5 is 30. So this is 30 times u squared. But this is supposed to be a function of x, not u, so we go back to x. So f prime of x is 30 times 5x minus 8. That would have been the red x we had before, squared. This is our slope formula. So our slope m should be f prime of 2. Remember, we're doing this all at the x value of 2. That's 30 times 5 times 2 minus 8 squared, which is 30 times 5 times 2 is 10. 10 minus 8 is still 2. That's 30 times 2 squared, which is 30 times 4, which is 120. So that's our slope. So remember, equation of line, y minus y1 equals m times x minus x1. If you don't remember that, shame. You need it. So the x1 and the y1 were the 2 and the 16. That's the x1 and the y1. So we go y minus 16 equals, the m was the 120 times x minus the x1, which was the 2. That's y minus 16 equals 120x minus 240. We're then going to add 16 to both sides, giving us our equation, y equals 120x minus, that's 224. So the slope is 120. The y-intercept would be 0, negative 224. And if you sketch the curve and the tangent line, you could see that it would be touching and going at the coordinate x equals 2. So we're going to call it a day there. We've done enough with this chain rule in our almost 2 hours. I don't really want to introduce the last section, which is on higher order derivatives, but I'll say for 10 seconds what it is. A higher order derivative is taking a derivative of derivative. So we're going to get into things like a y double prime or an f double prime or an f triple prime or an f quadruple prime. And there's even some interpretations as to what some of those things mean when we talk about real world concepts. Specifically, the main thing we get into is position, velocity, and acceleration. All three of those are related to each other by calculus. If you have an equation that describes the position of something moving, you can find its speed and its acceleration by doing calculus on that thing, specifically by doing derivatives. But we'll save that for next time. So we did exactly what I hoped we would do today, and we finished 1.7. So that homework will be due in a week, which is the 11th. We'll finish 1.8 next time. We might even get a little into chapter 2. We will probably get into chapter 2. So that'll be due on the 16th. So this test 1 date, we will not have an issue hitting. That'll be the 3-day window you'll have to complete it. Whether I upload that into my math lab or distribute a paper test for you to work on, that'll be determined. I'm still figuring that out. But if it is in my math lab, it would be 2 attempts. And I didn't say that earlier, but 2 attempts if in my math lab. I take the best grade. If it's a paper pencil test, you only get 1 attempt because I'm not going to do 2 full grades of a paper pencil test. I would never have any free time in my life. So there we go. If you have any questions, please email me. Please work on that homework. Please purchase your access kit if you have not. It has been 2+ weeks by now, so a lot of people's access was ending on the 3rd and the 4th. And you won't have access to your homework, and you might not have access to test materials. Definitely at some point, if not this one. I'm definitely going to do some tests in my math lab whether it starts with test 1 or not. So have a good weekend, study hard, get some homework done. Remember, you should be putting 8 to 9 hours of work outside of this class, outside of the lecture, to say that you're really, really, really trying. And if you ace everything in 4 hours and you don't need the extra hours, that's fine. But if you're still struggling after 4 hours, invest the time, or you can't say you've tried, because that's the expectations. All right, much love for y'all. Have a good weekend. We'll see you on Tuesday.